When you book an Uber, dozens of things happen simultaneously. The driver is assigned, your payment is processed, a notification is sent, the trip is logged for accounting, fraud detection runs in the background. None of these happens synchronously in a single API call. They can't. That would be too slow and too fragile. Instead, a message is placed on a queue, and each downstream system processes it independently at its own pace. This is the pattern of message queues and event streaming. It's one of the most powerful architectural tools you have, and it's central to the design of almost every large-scale system. Today we'll cover message queues, event streaming, the key differences, and when to use each. Understanding this topic well is what separates candidates who design systems that merely work from those who design systems that are resilient, extensible, and built for the real conditions of production traffic. Without message queues, services call each other directly. Service A calls Service B, waits for a response, then calls Service C, and so on. This synchronous coupling creates problems. If Service B is slow, Service A is blocked. If Service C is down, the entire chain fails. If you suddenly need Service D to also react to what Service A just did, you have to modify Service A to add a new call. Message queues break this coupling. Let's make this concrete. Imagine an e-commerce checkout flow. The order service receives a purchase request, calls the payment service to charge the card, calls the inventory service to decrement stock, calls the notification service to send a confirmation email, and calls the analytics service to record the event. If any one of those downstream services is slow or unavailable, the checkout fails. The customer sees an error. You lose the sale. Worse, the services are now tightly coupled. A deploy of the notification service requires coordination with the order service because they share a synchronous contract. This is the architectural trap that message queues are designed to escape. A message queue has three components: producers that send messages, the queue itself that stores them, and consumers that process them. The producer publishes a message and moves on. It doesn't wait. The queue persists the message. The consumer picks it up when ready. If the consumer crashes mid-processing, the message stays in the queue and is re-delivered. No message is lost. This gives you several powerful properties. Load leveling, burst traffic fills the queue, consumers process at a steady rate. Fault isolation, a failing consumer doesn't affect producers, and retry logic, failed messages can be requeued automatically. Load leveling deserves more attention because it's one of the most underappreciated benefits. Without a queue, your order service must be provisioned to handle your peak traffic. Black Friday, say, at 50,000 orders per minute. With a queue, you provision your downstream services for your average rate, 5,000 orders per minute, and let the queue absorb the burst. The queue depth spikes during the peak and drains over the following hours. Your infrastructure costs are dramatically lower. This is exactly how Amazon's order processing pipeline works. The checkout service publishes orders to SQS. The fulfillment workers, running on auto-scaled EC2, drain the queue at the rate they can sustain. During Prime Day, the queue depth can reach millions of messages. It drains over hours without any service degradation. The dead letter queue pattern is critical for production robustness. Without it, a single malformed message, a so-called poison pill, can block your consumer indefinitely if it keeps crashing on processing. The DLQ gives you a safety valve. After N retries, move the message aside, alert your team, and keep the main queue flowing. One critical concept for interviews: delivery guarantees. In practice, use at least once with idempotent consumers. Design your processing logic so that processing the same message twice produces the same result. This is simpler to build than exactly once and works for most use cases. Idempotency is worth understanding precisely. If your consumer processes an order fulfillment message and the message is delivered twice, the second processing must not fulfill the order again. The standard pattern is to include an idempotency key, a unique message ID, and check it against a store of processed IDs before acting. If already processed, return success immediately without side effects. AWS SQS provides at least once delivery and uses a visibility timeout mechanism. When a consumer receives a message, it becomes invisible to other consumers for a configurable period. If the consumer crashes without deleting the message, it reappears after the timeout and gets redelivered. Consumers are responsible for deleting messages after successful processing. Message queues are great for task distribution. One message, one consumer. But what if you want multiple independent services to all react to the same event? And what if you want to replay past events? That's event streaming. Kafka is fundamentally different from a traditional message queue in 3 ways. First, messages are not deleted after consumption. They're retained for a configurable period, days, weeks, or forever. This enables replay. You can reprocess all historical events if you deploy a new service or fix a bug. Second, Kafka supports multiple independent consumer groups. Every consumer group gets its own position in the log and reads all messages independently. Publish one event, 10 different services all consume it. Third, Kafka partitions topics across multiple machines for horizontal scale. Each partition is an ordered log. Parallelism comes from adding more partitions. Let's go deeper on partitions because this is where Kafka's performance comes from. A Kafka topic can have dozens or hundreds of partitions. Each partition is an ordered, immutable, append-only log stored on disk. Producers write to partitions in parallel. Each consumer group assigns partitions to its consumer instances. At most, one consumer per partition per group. So a topic with 32 partitions can be consumed by up to 32 consumers in a group in parallel. This is how Kafka achieves millions of messages per second. The parallelism is architectural, not magic. You configure it by choosing the number of partitions when you create the topic. More partitions means more parallelism. Choosing partition count is a capacity planning decision that you'll need to be able to discuss in interviews. Kafka's durability model: each message is written to disk and replicated to a configurable number of broker replicas, the replication factor. With RF3, Kafka tolerates 2 broker failures without data loss. The in-sync replicas list, ISR, tracks which replicas are caught up. A producer can configure actual to wait for all ISR replicas to confirm before considering the right durable. Knowing when to use which is a question you'll face in case study interviews. Use a message queue, SQS RabbitMQ, when you need point-to-point messaging, tasks that are consumed by one worker and then gone, or simple retry logic with dead letter queues. Processing jobs, sending emails, triggering webhooks. Use event streaming, Kafka. When multiple services need to react to the same event independently, you need event replay for new services or debugging. You're building an event-sourced or audit log system, or you need high-throughput time series data pipelines. Here's a diagnostic question you can use in interviews to decide. Does the event need to disappear after one consumer handles it, or does every interested party need to see it? A background job to resize an image after upload. That's a task for a queue. One worker picks it up, resizes the image, deletes the message. Done. A user sign-up event that needs to trigger a welcome email, a CRM update, an analytics event, a fraud check, and a referral attribution. That's an event. 5 different services need to react independently. That's Kafka. Another deciding factor is replay. If you ever anticipate needing to reprocess historical events, rerunning analytics, backfilling a new service with historical data, auditing past activity, you need Kafka's persistent log. A message queue is gone after consumption. You cannot replay it. Here is how to deploy this knowledge in an interview. The rule is simple. Anytime you have an async operation, reach for a message queue or event stream. Do not wait for the interviewer to suggest it. When you see these signals in an interview, propose a queue or stream. Any operation that doesn't need to complete before the API response returns. Email sending, analytics logging, thumbnail generation, notification dispatch, audit logging. Any operation that could spike in volume and overwhelm a downstream service. Batch processing, import jobs, report generation. Any operation that needs to fan out to multiple downstream consumers. Order placed, user signed up, payment completed. The framework for choosing queue versus stream. If one consumer handles one message, use a queue, SQS, RabbitMQ. If multiple independent consumers need all messages, use a stream, Kafka. For delivery semantics, default to at least once with idempotent consumers. Only reach for exactly once if you're dealing with financial transactions and cannot tolerate any duplication even with idempotency keys. When the interviewer asks, "How does your payment service scale?" the answer is, the payment service consumes from a queue. It scales horizontally by adding consumer instances. The queue absorbs bursts. No payment request is dropped. This is a complete, defensible answer that demonstrates production-level thinking. These numbers give you the credibility to make specific, defensible claims in interviews. Kafka handles millions of messages per second per broker. LinkedIn runs Kafka at over 7 trillion messages per day across their infrastructure. A single Kafka broker can sustain throughput of hundreds of megabytes per second. Kafka latency for a producer write with Ep.9, leader only, no replica wait, is under 10 milliseconds. With Ep.all, full replication, typically 20-30 meters on well-configured clusters. Kafka default message retention is 7 days. You can configure it to retain indefinitely for event sourcing use cases. Storage is cheap. Event logs are worth keeping. RabbitMQ handles approximately 50,000 messages per second on a single node in standard configurations, making it appropriate for moderate throughput task queues, but not Kafka-scale event pipelines. Amazon SQS supports a standard queue throughput of unlimited messages per second, standard queue, and 3,000 messages per second, with batching for FIFO queues. Standard queues are the default choice for most async task processing. Consumer lag is the key operational metric for Kafka, the number of messages in a partition that a consumer group has not yet consumed. A growing consumer lag means consumers are falling behind producers. You need to add consumer instances or optimize processing. For sizing, if your system produces 100,000 events per second and your consumer processes 10,000 events per second per instance, you need 10 consumer instances minimum. With RF3 and 32 partitions, you can run up to 32 consumer instances in a group. Plan partitions at 2 or 3x your expected peak consumer count to leave room to scale. Message queues decouple producers from consumers, enable load leveling, and guarantee delivery. Use SQS or RabbitMQ for task queues with single consumers. Event streaming Kafka enables multiple independent consumers, event replay, and high-throughput event pipelines. Use it when you need pub/sub at scale. The choice between at most once, at least once, and exactly once delivery depends on your tolerance for duplicates versus data loss. The interview heuristic is decisive and simple. Any async operation in your design should route through a queue or stream. Never have services waiting synchronously for operations that don't need to be synchronous. In the next video, we cover rate limiting and API gateways, the mechanisms that protect your system from being overwhelmed by too many requests. Every public API needs rate limiting, and knowing the algorithm's code is a signal that separates senior candidates from mid-level ones. See you in video 10.